just get, there we go, great. Let me get a feel for the age, like the academic age range of people. How many freshmen are here? Raise your hand if you're a freshman. Everyone should be sort of well versed with Zoom. Okay, oh, I see. Okay, 3 people, 3 or 4 people. And sophomores? So yeah, so unraise your hand if you're a freshman, raise your hand if you're a sophomore. Juniors? Okay, good. And seniors? Everyone else is senior. Okay, so largely juniors and seniors and a smattering of younger students. All right, so this talk is usually, I mean, this kind of thing is usually more fun in person than via Zoom, but it would be more fun if you interrupt me with questions than if I'm just talking to like a screen. So feel free to jump in with questions throughout the talk. Let me get screen sharing going. Let's do this. Yeah, and okay. Do you see the notepad, blank notepad?
Yes.
Okay, very good. So today I want to tell you about something which is, I mean, in a sense, it's very much the way theoretical physics works, because it's something we're trying to write up now, but it's still something we're trying to understand. So I think it's kind of interesting and kind of fun, but it's not, some fully formed, complete set of ideas yet. So I want to talk about gravitational signatures of extra compact dimensions. So I've given a couple of talks like this in the past, where, I mean, like this meaning to a broad audience on aspects of string theory and theoretical physics. And usually what will happen is we have a lot of fun getting to the basics of why string theory is interesting, and then we run out of time to sort of see what's cutting edge. So today I want to try and do it a little bit differently and spend less time explaining the motivation and more time explaining roughly what we're trying to aim for, because it's pretty concrete at the end of the day. So the first question you should ask is, what do you mean by compact extra dimensions, and why should anyone care about the possibility of compact extra dimensions? And for that, we do need some motivation. So we'll need some insight from string theory. This is a very informal talk, as I just said. So it's not in any way some kind of polished presentation. So I want to just remind you how you arrive at a picture of gravity, both at the classical level and the quantum level, and what it means for things that we might be able to observe in nature. So as you all know, the speed of light is as fast as you can go. What's the speed of light? Somebody tell me.
1.
1. That's right. There's a theorist in the audience. And if you're not a theorist, but an experimentalist, what would the speed of light be?
300 million meters per second.
300 million meters per second. So 3 times 10 to the 8th meters per second. So the speed of light is a controlling constant of nature for how relativistic the world looks. So as your velocities get very, very high, so as v over c goes to 1, the laws of physics change. They become relativistic. Let me just abbreviate everything now. Whoops, don't want to do that, need to do that. Let's see. As a hallmark of the change of becoming relativistic, what happens to the addition of velocities? If I add 2 velocities together, how does that get modified? Who's prepping for the GRE?
V1 plus V2 over like 1 plus V1 times V2 over C squared or something?
And what physically, that's right, what physically should be the characteristic of this modification of Galilean addition of velocities? So Galilean addition of velocity, just add velocities together. But you've given a modification of that formula, which does what physically?
Sure, nothing can go faster than light.
Yeah, if I try to add C plus C, amazingly, I get back C. So I can't go faster than the speed of light thanks to that denominator. So we have a very sharp contrast with Galilean physics as speeds get very high. Give me another constant of nature. Juniors should have seen this one.
H.
Yeah, and in fact, in theory, we often like to think about H bar rather than H, which is H over 2 pi. What is that, actually, approximately? I mean, it's actually a measure.
6.626 times 10 to the minus 34 in KGS.
Okay, I'm going to give it in slightly different units. I'll
MKS.
do
MKS.
MKS. So I'll do 6.58 times 10 to the minus 16 electron volt seconds. But most importantly, it's not zero. And because it's not zero, it's telling us that the world is intrinsically quantum, that our position and our momentum don't commute. The world is a quantum place. And when you study quantum mechanics, and some of you are taking quantum with me this quarter, you learn that instead of having absolutes, like I hit a ball, the ball goes flying off, there's really some wave function that's describing probabilities, like the probability, a probability density in this case, that you would measure some outcome given by a wave function. A very different departure from classical physics from relativistic, from Newtonian physics from relativistic. Give me another constant of nature. Any other constant? This one freshmen should know.
Universal gravitation. Oh, oops, sorry.
Yeah, yeah, big G.
Well, I'm a junior.
Okay, so even better. It would be better if the juniors and the seniors also knew what the freshmen knew, but people forget also. Big G, which is governing the strength of gravitational interactions, which is approximately what? Anyone?
I guess
This is what I want.
6.67 times 10 to the minus 11.
Times 10 to the minus 11. Good. And what units should that be in?
Newtons times meter squared over kilogram.
Yeah, because you want Newton's force law for gravity, that the gravitational force is given by big G times the product of the masses of the objects that are gravitating divided by the distance squared between them. And for those units to work out, you want to have a unit of force in the numerator, newtons. You want to cancel the meter squared in the denominator, and you want to divide by the mass squared. So that gives you that set of units. So if you have some mass m1 and some mass m2, and they're separated by some distance r, you get a universal force. What sign does that force have? Repulsive?
Yeah.
Attractive? Does the moon stick around the Earth, or does it fly away?
No, it's repulsive.
It's repulsive. If it were repulsive, what would happen to the moon and the Earth? What would they want to do?
Brain fart, sorry. Attractive.
Attractive. Because you want to have an attractive force. That's what keeps things in orbit. If it were
I think I
repulsive,
said one thing, but I meant another.
all right, that happens all the time. Happens to me all the time. Attractive. What now? In electromagnetism, you have both positive charges and negative charges, and if you have a positive charge and a negative charge next to each other, what's the sign of the force there? Attractive or repulsive? So let's just say, is it attractive or repulsive?
Attractive.
Attractive. And how about for two like signs, two plus signs, say, or two minus, two electrons? Attractive or
Repulsive.
repulsive? They want to fly apart. Do you know of any? Do you know of any charge for gravity that would be repulsive? Have you ever heard of
Negative
anything?
mass?
If you had negative mass, you could do it. But we don't know what negative mass means, and we've never seen anything with negative mass. So all sources of energy gravitate, but they gravitate with the same attractive force. So here you have a universal attractive force, which is kind of weird compared to electromagnetism. So this story is all due to Newton. And you could ask the question immediately, how can you make Newton's laws of gravitation say compatible with special relativity, with the physics of going close to the speed of light? Because as it stands, it's not compatible. So this was a puzzle. If you believe in relativity and you believe we can measure the law of gravitation, we can see how the moon goes around the earth goes around the sun, all the planets go around the sun, how they perturb each other's orbits a little bit to really remarkable accuracy. We should be able to make the laws of physics compatible with one another. And the person who did this was Einstein. So Einstein took Newton's laws of gravity and he modified them as follows. So Einstein made them compatible. How did he do it? Well, what Einstein realized is that the only way in which you could make them compatible with one another is if space-time itself distorts with stress energy. Let me explain what that means. You go to Home Depot, you buy yourself a ruler, the ruler has its ticks on it. 1 meter, 2 meters, whatever, or feet probably from Home Depot. If you buy a clock, the clock ticks 1 second, 2 seconds, 3 seconds, 4 seconds. Your iPhone is ticking away, or your smartphone, or whatever you're using for a clock. But that's not quite accurate. Because you're holding your phone in your hand when you look at it, your mass, which is a distribution of stress energy, changes in a very, very tiny way the rate at which the clock ticks. And what Einstein realized is that all stress energy of any kind will change the way clocks tick and will change the ticks on a ruler depending on the distribution of that stress energy. So this is all classical physics. There's no H-bar in the story. It's all classical. But what he realized is space-time distorts with stress energy. It's classical. This is classical. Let's stress that. So it's classical, but relativistic. So you could take some mass. Here's my mass distribution. What that mass distribution is doing, and you're doing this, and every piece of stress energy in the universe does this, is in a very tiny way, it's distorting the way in which we measure things, which is determined by a metric. So when you learn special relativity, you implicitly were studying the Minkowski metric, which means that your notion of distance was determined basically by a 4x4 matrix. And that 4x4 matrix gave you what's called a metric. So this is a metric. So the metric for Minkowski spacetime is very nice. It's minus dt squared plus dx squared plus dy squared plus dz squared. So the Minkowski metric is what you study when you study Lorentz transformations and boosts, and what happens in special relativity when you change frames at different velocities. How you relate the physics in one frame to to the physics of an observer in a different frame, so that they're observing the same event and they can coordinate their observations and realize that it's just a change of observer, but it's the same physics. Something blows up over there, you observe it, somebody running by observes it, they can both say it's the same thing. General relativity, which is this generalization of special relativity to include gravity, makes things a little wilder. So instead of just having this notion of a metric, and this Minkowski metric, let me write it out. I'm going to write a notation which won't make sense yet, but hopefully it will be schematic. It's a 4x4 matrix because it's giving you a quadratic form. And that 4x4 matrix is diagonal in this case, has entries minus c squared, plus 1, plus 1, plus 1. So minus c squared would be acting on, say, time, and this will be the space directions. And then you could contract the transpose of that vector to get that quadratic form. So that's the sense in which a matrix is determining a metric. Now we can write this a little more generally. So we can take our notion of a ruler and encode it in this metric, which is now a more general 4x4 matrix, but it's a 4x4 matrix that will actually depend on position and time. So, whoops. So this will be contracted with x mu and x nu, which will be our space-time coordinates. So let me fill this in a little bit. So this will be, for example, g00 xt dt squared. I'll just put a few entries in, plus g01 xt dt dx plus g11 xt dx squared plus dot 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 dot. You sum over all of those indices. So here x mu are your 4 coordinates. So that's time. I wonder if I should have some kind of c in. So I'm going to be very sloppy with c's, putting c's in the right place, because in theorist units you set c to 1. So space and time can be exchanged if c is set to 1 by multiplying by a factor of c. So maybe this should be ct, actually. Okay, x, y, and z. So it's one thing to claim that the rulers and the clocks that we use are getting distorted by stress energy, but you need to have a formula for how they're distorted. And that was Einstein's great realization. His realization was that what is actually now called the Einstein tensor, which is a 4x4 matrix, if you wish, which is a measure of the curvature of space-time. So for the Minkowski metric, this would just be 0, for example, because the Minkowski metric doesn't change as you change positions. But you can imagine computing something like the acceleration of this metric g mu nu. And if you computed the acceleration, it would give you something like this Einstein tensor. So it's telling you how does that metric change as you move around in space and time. So we'll just call that curvature of space-time. And that is determined by the distribution of stress energy in the universe. So this is the stress energy tensor. This is telling us where the energy is located in our universe. Whoops, what did I write? Stress energy tensor. That's Einstein's equations. And this is his theory of general relativity. It's an incredibly beautiful theory. It's totally self-contained. It's a classical theory. It's a statement about how gravity gets modified, Newton's laws get modified when physics becomes relativistic. And it doesn't require any h-bar, it doesn't have any h-bar in it as it stands. And it's simply a statement that our notions of clocks and rulers get distorted when there's energy present. Energy as small as u. So all of us together have a very tiny distortion on the clocks and rulers around us. The sun is a much bigger distortion. And in fact, it's that distortion that gives rise to the force that we think of as gravity. So you can think of gravity as a force, or you can think of it as a warping of the background space-time metric, which produces what looks like an attractive force. Very neat. Questions on this part so far? Are people with me or lost or what? Just schematically.
Professor,
Uh-huh.
maybe go a little bit into the motivation behind like contracting indices in Einstein summation a little bit, especially for those who haven't been exposed to the summation convention yet.
You mean like this thing? Oh, sorry. This thing.
Yeah.
Like this guy. Yeah. So
Yeah.
this is a shorthand for writing out this complete sum over all of the space-time coordinates. So here we're going to be summing over everything from 0 to 3 in this case, 0, 1, 2, 3, which are running over time x, y, and z. And we could write out that entire contraction, g00 dt squared, g01 dt dx, etc., or write it in this shorthand where a lower index and an upper index repeated are just summed over. So it's really a convenient shorthand for saving us from writing out a ton of indices. Does that make sense? Is that reasonable?
Yeah, thank you.
Okay, there is a stunning prediction of general relativity. And the stunning prediction, anyone guess? No takers on the stunning prediction?
Black holes? Or
Black holes indeed. Who said that? I actually can't see who's talking on this thing.
me, Srihari.
Ah, okay, good. Yeah, good. Hi.
Hello.
So the stunning prediction is indeed black holes. What are black holes? Well, black holes were some of the earliest solutions to this set of equations that Einstein wrote down, and they're solutions that are vacuum solutions. So you set T mu nu to 0, no stress energy. Bizarrely enough, if you set the stress energy to 0, there is still a really interesting vacuum solution found by Schwarzschild. Which now, here's the bizarre part. Even though there's no stress energy, we're solving a vacuum equation, this solution will have mass m. So it's an object. It's something that carries mass. And I'll write down the metric. So the metric is, I'm just going to call it g. It's going to have a time component, which looks like this. And put these C's in, if I remember where they go, plus a radial component, which looks like the same factor, but to the -1 power. And then there's a sphere, a two-sphere. Let's call it a two-sphere metric. We don't have to write it out. It's, well, okay, maybe I'll write it out. Everyone's comfortable. D theta squared plus sine squared theta d phi squared. This is a funny looking metric. It's got this parameter in it, the Schwarzschild radius, R sub s, this thing that sits here. And something weird seems to happen when you come in from infinity, which is R very, very big, you approach the Schwarzschild radius, Rs. At that point, at some point, it looks like your metric goes haywire because the thing that measures your clock, your dt squared term in the metric, vanishes. So naively, it looks like this metric is sick at that point. But it turns out that sickness is just the coordinate artifact. And if you change coordinates, there's actually no sickness at this point, Rs, and the metric is smooth. So there is actually a singularity, but the singularity is not at Rs, but it's at R equals 0. So you can think about this. Oh, it always switches this. Okay. You can think about this as some object. It's a vacuum solution. There's this radius RS. And if you were coming in from infinity, you would cross RS and you actually look at what happens to space-time. Nothing very special happens to space-time. On the other hand, you would be in big trouble at this point, and we'll see why in just 1 second. We'll also note that RS, if you try to measure the mass of this spacetime, and there's a way to define mass in general relativity, which is quite general, you'll find that this RS is proportional to the mass. So the bigger the black hole, this is a black hole solution, the larger its mass, the larger this Schwarzschild radius is. So what's happened is when you cross this location RS, that's the location of an event horizon. Which means that once you're in, you'll never get out. And by you, I mean anything. Light goes in, it never gets out. So once you cross this, you're trapped inside this object, and you will gravitationally eventually fall into the center, where you'll experience some enormous tidal force, and classically you'll be crushed like a bug in the middle of this thing. Well, this is kind of interesting that classical general relativity has such solutions. So we can just estimate how big this Schwarzschild radius is. So for the Earth, for example, this is like 9 millimeters. So if you wanted to make the Earth into a black hole, you'd have to compress all of us and everything on the Earth into a volume of a sphere of size, roughly 9 millimeters. Pretty tiny. So we're a long way from a black hole. The sun is a little bit better. Its Schwarzschild radius is of order of 3 kilometers. Still not great. The sun would have to have a lot more matter collapse into it to reach the point where it will turn into a black hole. So you can fall in, but classically never get out. Very beautiful classical situation. Okay. Questions on this stuff?
Professor?
Mm-hmm.
What do you mean, like, classically never get out?
I mean, as long as h bar is 0, there is no way for you to escape. So if you're Bob Wald and you choose to keep h bar 0 because you're a classical relativist, you will fall into the black hole and you will be trapped there forever. You'll be crushed like a bug. Now, quantum mechanically, it's a different story. There's a way to escape as radiation. And that leads us to some very beautiful and deep questions in theoretical physics. But today I actually don't want to go down this road of the information paradox. We'll look at some different aspects of black holes. So Hawking's great realization was that black holes will actually radiate. I mean, they radiate basically black body radiation with a temperature. And that temperature goes up as the black hole gets smaller, radiates away more mass. So a very big black hole is very cold. And it just starts radiating away very slowly. And as it gets smaller and smaller and smaller, it radiates away all of its constituent mass. And then the end state was unknown, or is unknown, I should say. So there's all kinds of issues there with unitarity, because black body radiation has no information of what fell into the black hole. What did you make it from? But we know from quantum mechanics that we expect the world to be unitary. And reconciling those two statements has been a big driver of a lot of theoretical work for, I don't know how long. Very long time. 60s, maybe? I don't know. Very, very long time. Long before I was born, I think it started. Good. Other questions? Okay. Now let's turn to quantum gravity. So from our fundamental constants of h bar, c, and big G, we can form one mass scale called the Planck scale, or the Planck mass, if you wish. You can also form one time or one distance, but I'm just going to use mass here. And it's of order 10 to the 19th giga electron volts. What's giga? What's mega?
I think it gets 10 to the 9th, but I could be wrong.
That's right. Giga is 10 to the 9th. Mega is what?
10 to the 6th.
10 to the 6th. A kilo electron volt will be what? keV. 10 to the third. Good. Let's just orient ourselves with what kind of energy scale we're talking about. What's the energy scale for semiconductor physics, roughly? Just order of magnitude. Like the gap in the metal, say, or the gap in a semiconductor between like insulating and conducting bands. How many EV are we talking? Kilo electron volt, mega electron volt, giga electron volt. Who's taking condensed matter? Who's taking the solid state physics? Take that as nobody. So you want to make a random guess? Huh?
I am taking solid state physics.
Okay. What roughly is the energy scale? What order is the energy scale?
Ah. X-ray level?
So you're thinking of like atom spacing.
Yeah.
But what kind of energy do you need to put in for excitations in, say, a semiconductor? Like if Intel is worried about building transistors, they're usually not using X-rays, right? Isn't this like of order EV, roughly? Whoops. Of order EV?
I wouldn't know.
Yeah, it's of order EV. On the other hand, if you look at the biggest particle accelerators in the world, like the Large Hadron Collider in CERN, anyone have any idea what center of mass energies roughly they're playing with?
It's like a TeV, right?
Like a TeV, indeed. What's T? So giga is 10 to the 9th. T is the next one up. What should the next one up be?
10 to 12.
Peta?
10. Peta would be above that. T is the next one. It would be 10 to the 12. So if we look at the energy scales of collisions in the highest energy collisions that we study today, we're talking of order 10 to the 12 electron volts, but the fundamental scale of quantum gravity is given by this quantity, which is horrifically bigger, right? I mean, it's just, TeV is like probing the GeV part of this. Forget the 10 to the 19th part of this. So you've got such a massive hierarchy between the fundamental scale in nature and our observations that it might seem hopeless that we could actually observe anything to do with quantum gravity. But we kind of have gone a long way without experimental guidance, but just based on theory, which is kind of remarkable that we can go as far as we've gone on just trying to build a consistent theory of quantum gravity. So what we think is true today is we believe that string theory is the right theory of quantum gravity. But we don't understand how to describe our world properly yet within string theory, for some reasons that I'll sketch in a moment. But the idea is basically the following. Suppose you just have an electron sitting there. If you watch the electron over time, it might just do this. It will follow some world line. It's a point particle for our usual approximation. What we're doing in string theory is replacing this with a little string. So you imagine a little string sitting there, a little loop of closed string. If you follow this over time, oh, I will draw this very badly. Okay, that looks like just a blob. Let me redraw this. Okay. So just imagine there's a little loop of string, and it does this roughly. It will sweep out some wall volume. Now, we're not interested in just any old loop of string, like your favorite elastic band. The string itself will be characterized by some tension, just like an elastic band has some tension. When you pull it, there's some resistance to stretching it. And that tension has a mass scale. I'll just call it the string scale, M string. This elastic band, however, is relativistic. So it's a relativistic string. It moves at the speed of light. When you quantize that string, you find, surprise, surprise, a graviton, which is not just something out of Star Trek. A graviton is supposed to be the force mediator for gravity. So when the world becomes quantum, and now we've introduced h-bar into the story to get to quantum gravity, all waves can be viewed as either waves or particles. And the particle nature of gravity, so we have gravitational waves that we can observe with observatories like LIGO, and we'll come to LIGO in just a moment. But at the same time, there's a particle nature. And the particle that mediates gravity is the graviton, which is a spin 2 particle. It's very hard to write down a quantum theory of a spin 2 particle, massless particle. In fact, there's no other known quantum theory of a spin 2 massless particle beyond this one, which is why many of us are strongly convinced this is the right theory of nature. It's so severe theoretically to write down a consistent theory of this type that there basically are no other possibilities. But this theory has a very strange prediction. The prediction is that the universe itself has 10 dimensions. I'm going to write the 10 as 9 plus 1. These are dimensions. So that 1 is time, and that 9 is space. So what we discuss in physics that you've seen throughout your undergraduate experience is a world that involves 3 spatial dimensions and 1 time dimension. But string theory doesn't make sense in 3 space and 1 time. It only makes sense perturbatively in 9 plus 1. So I'm going to stress that this is perturbative. Perturbative in what? Well, in addition to the graviton, there's always a scalar field, a scalar mode called a dilaton. And the expectation value of that dilaton is roughly the interaction strength of the string. So the interaction strength of the string is in some sense dynamical. It's set by the value of a scalar field that can fluctuate, which is kind of interesting and strange because there's no other free parameters in the story. But it turns out that if you go beyond perturbation theory, and this is like saying, and the analogy you should think of is if you took a function like e to the alpha x, and all you knew is the expansion for small alpha, the first couple of terms, as alpha goes to 0. But you didn't really know what that function was. If you actually knew what that function was, you would have a much deeper understanding of the theory. And what we've learned is when you go beyond this weak coupling perturbative expansion, that the scalar field itself can be thought of. Beyond perturbation theory, one can think of phi, the scalar field, the dilaton, as in one case anyway. I'm kind of cheating in some ways, but cheating in ways that are hopefully innocuous. Can think of phi as the size of a hidden circle. And so phi itself, instead of being this extra scalar field that is lurking in string theory, we can think of string theory as part of a bigger picture at the non-perturbative level. There are 10 spatial and 1 time direction dimensions. So what we think is that fundamentally the universe is 11-dimensional. And fundamentally, perturbative string theory is replaced by a bigger theory, which is called M theory. I'm running out of time, right? I'd like to get to the new stuff. So, let me explain, about a slide or two. I'm going to explain things a little more picturesquely with a little less detail, so we stay within time. So, okay.
It's okay if we go a little bit over.
If we go 5 or 10 minutes over, I mean, it would be, I think, more than 5 to 10 minutes at most.
Yeah.
Okay, and people can feel free to bolt if you know you're falling asleep or whatever. So this M theory itself, is very mysterious still. We know things about it without knowing any fundamental definition. It's a very deep, open problem of finding something like Einstein's principles of every observer should be physically equivalent and relativity makes sense. You can't go faster than the speed of light. That set of principles to define something like M theory is missing at the moment. But we understand a lot about it in different corners, when it reduces to a string theory, when we compactify it in different ways. But all of this motivates a very basic question. It motivates gravity with extra compact dimensions, which was the title of this talk. And so one way we might hope to test something like string theory is to see, can we see some signs of those compact dimensions in observable physics? Now, I explained to you already that the fundamental scale of quantum gravity is incredibly big compared to any observable scale today. So that looks like a hopeless task. But we have this very beautiful counterintuitive argument from black hole physics, because when you take quantum mechanics, you learn that wavelengths get smaller as your energies get higher. So you probe shorter and shorter distances. But black hole physics tells you the opposite. That Schwarzschild solution we looked at gets bigger and bigger as the mass of the black hole gets bigger. So somehow the intuition from high energy physics that high energy means short distance gets inverted into a statement about, in gravity, about high energy means large objects and long distances, which is a little bit weird. So let's follow our nose. Let me sketch a much simpler case. So let's take our normal space-time, which I'm going to denote as R31, 3 space and 1 time, and let's just add a circle of some radius r. If we're looking at physics in this 5-dimensional space-time and the circle is tiny, you wouldn't know it. You would just see stuff propagating around in 4 dimensions, and you wouldn't see any sign of the 5th dimension. The way to think about it is, imagine you had a really thin wire, tiny wire, very long but thin wire, and you lived on the wire. You would move up and down the wire. You would think the world is 1-dimensional spatially, but if you could really probe that tiny little circle, the circumference of the wire, you would realize, no, it's really 2-dimensional. So our intuition for this story should be, when the radius of that circle is very, very small, we can reduce everything back to physics in 4 dimensions. And when that circle gets big enough, we might be able to see some sign of it. Or when our physics becomes high energy enough, or something more exotic happens. So this process of reduction is called Klutzer-Klein reduction. And let me put that in, let me sketch it more closely. The idea is the following. if you started in 5 dimensions with only a metric, so we got our matrix, let me put a tilde on it to denote 5 dimensions. G, M, N, where M and N are running from say from 0 to 0, 1, 2, 3, 4. Because we've got one extra dimension here, where 4 is the circle. Then you could decompose this into polarizations that are either lying in space-time, that would be your graviton, or polarizations with one leg on the circle direction, and let me call the coordinate y for the circle coordinate. From the point of view of 4 dimensions, this has one index, mu. This is what's called a vector, or a Maxwell field. We think of it as a Maxwell field. And the last possibility is both legs of the metric in the y direction. That thing would look like a scalar field. Oops. Sorry, let me kill this. Okay. So there's a way to rewrite our theory on the circle in terms of a theory in 4 dimensions with extra fields. In addition to your gravity multiplet, you've got a Maxwell multiplet and you've got a scalar field. So this specific Kaluza-Klein reduction on the circle was originally thought about as a way to unify gravity and Maxwell as coming from one theory in 5 dimensions. That was the idea. It doesn't quite work to do that, but it's it was a very interesting picture by Kaluza and Klein, I guess, originally. I think, I don't know what the time frames there were. But in string theory, we get a variant of this picture. And the variant looks as follows. You've got your space-time, R3, 1, but we have a lot of extra dimensions to play with. So we've got all these extra dimensions that curl up, either 6 or 7, if you're talking about either perturbative or non-perturbative string theory, 6 or 7 curled up dimensions. And our toy model will be the circle. Toy model will be R3, 1, again, cross a circle. Well, the circle has one breathing mode. So if you want to ask, you can ask the question, can I deform this internal space in a way that still solves Einstein's equations? And it turns out here, you could dilate the circle and it stays flat, which is solving Einstein's equations. So there's one, what we'll call breathing mode. On the other hand, for these more complicated geometries, here, there are many breathing modes. Many meaning like up to 10 to the 5th is, I think, the record of order 10 to the 5th breathing modes. So morally, we can still think about things in terms of circle physics. Okay, I think 2 more slides are done, if roughly, if you can hang around. So now let's turn to some of the exciting observations that happened in recent years. I will not draw this properly, but I'll try. So LIGO is a gravitational wave observatory here, and LIGO triumphantly saw the merger of 2 black holes. So how many people have heard the LIGO chirp? I mean, there's a waveform that you can listen to. I will try to draw the waveform, but I guarantee you it will be a very bad sketch. I think it goes up, then there's this ring down. So in the beginning, there could be 2 black holes some distance apart. They start to inspiral. By the way, it doesn't have to be black holes. It could be neutron stars too. And there's a really interesting difference I'm going to bring up in just 1 sec. Then they get closer together, they're inspiraling. And then at some point they'll merge. Oh, that's supposed to be this thing, which is really badly drawn. This part of the waveform should be when they're actually merging, but they're kind of oblate. So it's not spherical. But the black hole eventually wants to become spherical. So then it will ring down until it becomes spherical. And that's this little chirp at the end. And I highly recommend listening to these waveforms if you haven't heard it. This is one of the most amazing experiments. When I first went to a colloquium as a freshman at Cornell, the colloquium, one of my first recollections of a physics colloquium, I went for the donuts, but one of my first recollections was listening to Kip Thorne from Caltech at that time, proposing this experiment. And even as a freshman, it sounded insane. I mean, it's like you're going to measure displacements of 1/1000th the width of a proton in some accurate way to see these gravitational waves. And amazingly, so many years later, they did it. Just an incredible triumph experimentally to see this. So these can be black holes or neutron stars. All right, now let me sketch what I'm interested in. When you add the circle, let's just do the circle case. When you add the circle, there are two interesting features, two new features. And I'll end after sketching these features. One, and this was noted a long time ago. You have a black hole. Outside the black hole, you have no scalar field. Black holes don't support what's called scalar hair, or let's call it scalar hair. So these breathing modes of the internal space cannot be excited by a black hole. This is a result due to Bekenstein, a long time ago. On the other hand, a star could have scalar hair. Some kinds of exotic stars, don't see any reason why they can't have scalar hair. That's already kind of interesting. So that's feature one. Feature two is also kind of interesting. So if you had the circle sitting there and you had your black hole, let me put it in blue. No, that's terrible. That's should have been the other way around. Let's do the circle in blue and let's do the black hole in black. I thought it was a black hole. If the black hole has no dependence on the circle, imagine the circle being very small. So the black hole doesn't really know about the circle at all. It's basically uniform along the circle direction. So it actually looks like a black string wrapping the circle. We wouldn't know it because it has no features in the circle direction. But if you start making the circle bigger and bigger and bigger, eventually you'll find that this becomes unstable. And the black hole wants to have some structure in the circle direction. This is largely numerical, I should say, to see this instability. But the argument that there is an instability is a very famous result. So the black hole becomes unstable. And this instability is called the Gregory-Laflamme instability. Roughly, it's the statement goes as follows. When the circle is small enough, the black hole can't fit inside the circle. But if the circle was like 1 billion light years across, for all intents and purposes, the universe would look 5-dimensional to this localized Schwarzschild solution, and it wouldn't know that there was a circle at all, and it would have to look like a localized 5-dimensional Schwarzschild solution. So the believed endpoint of this instability, it's quite plausible that this is the endpoint, is believed to be a circle, some radius r, with a 5-dimensional Schwarzschild solution, a d=5 black hole. And there's an entropic argument for this too. If you look at the entropy of a black string in 4 dimensions, it goes like the mass squared of the black hole. If you look at the entropy of a black hole in 5 dimensions, the 5-dimensional version of Schwarzschild, it goes like the mass squared times square root of the radius over m. So for a fixed black hole of mass m, as you make the radius bigger and bigger and bigger, eventually, this is entropy. The entropy for the 5D black hole will win out, and that should become the stable configuration. So very approximately, we expect this to be 5D Schwarzschild. Okay. Shoot. What do I want to say? I want to say, last thing I want to say. So we have an interesting set of possibilities. We can ask the question, does the merger of a localized black hole, something with structure in the internal direction, sorry, the merger of a localized black hole can produce scalar radiation in addition to gravitational radiation. So this scalar hair can be emitted as waves when a localized black hole merges, as can the merger of stars that saw scalar hair. So who cares? Well, it's kind of interesting because LIGO in principle can detect, or maybe the next generation of, like Lisa, the next generation of gravitational wave interferometers can in principle, can detect scalar radiation in a way that we're actually outlining in this paper via something called gravitational memory. And I'll just draw what gravitational memory is. It's convenient to look at space-time from the point of view of what's called a Penrose diagram. It doesn't make sense. It doesn't really matter. Where you have a null infinity where light rays end up, go like this, end up here. And then maybe a past null infinity. And if you put two inertial objects at null infinity, as a gravitational wave passes by, they move apart a little bit and they stay there. That's gravitational memory. So there's a memory effect in gravity. And that memory effect is in principle measurable by LIGO. And also there should be changes in the waveform, that chirp form, which we haven't really thought about. I mean, we've largely been concerned about this memory issue right now. But there will also be issues about how the waveform itself changes. But what we're really looking for are enough augmentation factors that even given the fundamental scale of quantum gravity being extremely high, we might still be able to observe some features of it in exotic mergers of objects which are not exactly 4D black holes, but things which are more exotic, localized in the internal dimensions, or stars that merge into a black hole, which can't support scalar radiation, so they have to emit a lot of scalar radiation in the merger process. That's the basic idea. All right, there I should just end and take questions. Thank you.
If anyone has any questions, feel free to raise your hand and I can call on you. I'll moderate the question. Yeah, go for it, Jonah.
Hi. What is a memory?
So a memory, well, you know what memory is, right? Memory is the idea that you remember something. So here the idea is that this detector will remember the passage of a wave. So there's a classical phenomenon which was studied both, actually first in gravity, actually, strangely enough, but then in Maxwell theory, where test particles located, and they have to be located near infinity because of some issues with what's coordinate independent, what's gauge invariant. But if you put them near infinity, they will remember the passage of this wave going by a displacement. So if you had a lot of these waves going by over time, that displacement would build up and it could be observable. So there's actually proposed experiments to test this memory effect. What we're using is, the memory effect is roughly like the zero frequency part of that waveform. The fact that the waveform went by, some waveform went by. And we're sort of using that as the coarsest measure of the difference between black holes with compact extra dimensions and black holes without compact extra dimensions, just conventional ones. That's the idea. Does that sort of make sense?
Yeah, Abraham.
Hi. I was just curious if you could kind of go over the differences you were talking about between perturbative and non-perturbative like approaches, and where that plays out here.
Yeah. So that's more in the structure of string theory itself. So in most physics that you study, you are studying physics that is perturbative in some parameter. So for example, you could have a potential energy, which is harmonic oscillator type, say, quadratic. But that could be an approximation to something that had a quartic, for example. Or so actually, we could actually have some fun with a cubic. Let's do a cubic. Now, if alpha is very small, and you're only studying physics when alpha is very small, all you see is harmonic motion, right? That you study in your freshman mechanics class. But if we look at this potential when alpha becomes important, becomes big, or your displacement gets very large, x gets very large, you suddenly realize that you're looking at the wrong physics, because all of a sudden you don't have stable minima left because of this cubic. And because of this cubic, the potential becomes unbounded as you go to negative x. Like it runs away down toward minus infinity. So in string theory, the picture that emerged was there was some collection, there's some 5 strings that had been found in 10 dimensions. It's not really that appealing to have 5 different theories of everything, but there was one open string. It's called type 1. There were 2 heterotic strings, which are closed. Sorry, I shouldn't draw it like that. They're closed strings. So there's like heterotic with 2 different gauge groups that distinguish them. SO32. And there's something called the type 2A and type 2B closed strings. So you had all these potential theories of everything, which is not a fun place to be. But every one of them has a parameter, which is called the string coupling, which is roughly the expectation value of that scalar field. And you could tune it in 10 dimensions. So all these lived in 10 dimensions. But then you realize something very neat. You realize that if you took this 2A theory and you made the string coupling very big, so that's again going in a regime where you don't have a small parameter to expand it. So now either you have no idea what you're doing. Like when I took quantum field theory as a graduate student, at that time, my quantum field theory instructor was a guy named Sidney Coleman, who was really a character. And you asked him, what can you say beyond perturbation theory? Perturbation theory in charge or any parameter. And he would say, nothing. We have no idea what's going on. But then there was a huge revolution in the period between then and now, where we learned a great deal of what was going on for a certain class of theories when that parameter became very big. So in this case, sorry, not 2A, 2B. Sorry, not 2B, 2A. In this one corner of string theory, you realize you get an extra dimension. And your theory really was geometrically descending from something in 11 dimensions on a circle. Exactly the circle we discussed, just a circle compactification. And then we realized things about all the other strings, that this 2B is in a stranger way related to a torus compactification. That sounds strange because that seems to take you to 9 dimensions. But in some magic that I unfortunately don't have time to explain, you end up back in 10. And we realized this type 1 theory, type 1, was actually the strong coupling description of one of these closed string theories, the SO32 heterotic. And finally, we realized this E8 cross E8 theory is again this 11-dimensional theory, but not reduced on a circle, but reduced on an interval. And at the endpoints live these gauge fields, the kind of domain walls living at the endpoints. So what really happened is these distinct string theories in 10 dimensions all became part of one theory reduced in different ways from 11 dimensions. And it all fit together in one very beautiful framework. And that's, I think, to me, philosophically pleasing. We don't want to have 5 different theories of everything. We want one theory of everything. And all of the choices that seem to give perturbative limits are just different compactifications of that one theory. I don't know if that helps at all.
No, that was very helpful. Thank you.
Other questions?
Yeah, Hui-Ting?
Yeah. So going off from the last question, I was just wondering, what is compact about the extra dimensions that you were talking about?
Good. So they're compact in the following sense. When you study scattering in quantum mechanics online, for example, you can have a momentum for your wave function, which is anything. You can have any k for this guy. K can be big, small, whatever, but it's a continuous spectrum. On the other hand, when you study the particle in a box, your k's were quantized in terms of the length of the box. Some integer over L. K sub n, say. But this is a quantized spectrum. So that's the fundamental difference between something compact and something non-compact. The volume in this case is infinite. And the volume here is finite. It's of order L. So the circle compactification is just a box with periodic boundary conditions. That's it. But that means that you could, in principle, reduce to, say, the ground state, which would look like that. Maybe I'm doing wrong boundary conditions. And then you have harmonics with more nodes. But each of those harmonics, there's a gap to the next excitation, And when L is very small, so the box here is very small in size, that gap is very large. So you could just restrict reasonably to the ground states in the circle direction and ignore the excited states, which you couldn't really do in this situation with continuous spectrum, because you've got an infinite number of momentum modes. There's no gap in the story. So there's nothing that gaps you away from the ground state. It's an interesting, there are interesting models, largely due to Randall and Sundrum, in some contexts, which are non-compact but still have a lot of nice features like this box, called warped compactifications. That's another part of this story that I actually just didn't have time to discuss. Does that kind of help, or did I misunderstand the question?
Yeah, I think that helps.
Okay,
Thank
good.
Tobin, you have a question?
Yeah, I was wondering if you could kind of talk again about what the instability is, and if that how that relates to the kind of the end result that you're talking about of detecting the gravitational memory.
Yeah, let me also give an advertising pitch. Those of you who are not subscribers yet, I would encourage you to subscribe to the YouTube channel for the Kadnov Center. If you go to YouTube, there is a Kadnov Center YouTube channel, which will eventually be linked to the website. The website is redone shortly. But we're going to have a talk by Roberto Emperan. I'm not sure what the date is, but it will be upcoming, where I actually wanted him to overview this story, like what is known about black objects in high dimensions. But this one on the circle is a very famous case. And what's amazing is even this case is not well understood, really. There's open issues about it in classical gravity, namely the following. So the physical picture looks as follows. Imagine the universe has an extra dimension. So you're living in 5 dimensions. instead of in 4 dimensions, and you were Schwarzschild, you would still write down the Schwarzschild solution. It would just have different powers in it, but you would still write down a black hole solution. It would have qualitatively all the features you would expect from the 4-dimensional Schwarzschild solution. That's this solution when this radius is infinite. So the radius could be, 100 billion light years. How would you know that you lived on a circle? Well, that solution, the actual solution for the black hole, would deviate a tiny, tiny amount from the 5-dimensional Schwarzschild solution, but this basically would be the story. You'd be looking at this 5D black hole. Now, as you make this radius smaller and smaller and smaller, this solution develops a perturbative instability. So there's a mode that emerges there, which destabilizes the solution and makes it want to tend to something that looks more like this kind of collection of black holes. They're actually connected by filaments, I think. That's what they see in numerical simulation. Now, if you're not numerically simulating it, you could guess all this. And the guess goes from the entropy bound. So when this, let's use this, when this radius is very, very large, entropically, a 5D black hole is enormously more preferred than a 4-dimensional black hole or a black string, something just smeared over this circle. But as you start decreasing this radius, you'll reach a point where R is of order m here. There's some numerical factors here that I've omitted, just to sketch it. But when here, at least with these numerical factors, when R is of order m, you reach a point where the entropy becomes comparable, and then the 4D black string starts dominating. And that should have been the preferred configuration. And then there should have been an instability that takes you from here to here, or vice versa, depending on which way you change the radius. So that's this Gregory-Laflamme instability. And they argued it exactly in this way, and then they exhibited the perturbative instability in the story. What's amazing is that, there's no more general theory of this. There's a zoo of black objects above 4 dimensions, but that zoo is not well understood. In 4 dimensions, there's all kinds of uniqueness results that you basically always have a black hole characterized by its spin and by its electric charge. And we've been discussing the case with no spin and no electric charge, just pure mass, nothing else. But above 4 dimensions, those theorems don't apply. And there's a very rich collection of solutions. So even in classical relativity, above 4 dimensions, there's lots of open problems of this type. Does that help sort of sketch the instability?
So I guess what maybe this isn't like a good very well defined question, but what kind of values are we measuring in this circle dimension? Is it just
that's a very good question. So there's good. So there are bounds on the size of the circle dimension, which depend on what kind of physics you're looking at. So if you assume that just gravity, propagates in the extra dimension, and you assume none of the fields that give us electromagnetism or the strong force or the weak force, if none of those things propagate in the extra dimension, they're somehow localized, say here, then the size of that extra dimension is actually quite weakly bounded, surprisingly. It's of order microns, I think is the bound. On the other hand, if you assume all of the standard model physics, the stuff that gives us strong, weak electromagnetic interactions, propagate in the extra dimension, the bound is much tighter. It's orders of magnitude tighter. I think it's, so I'm forgetting the number. The number will be in the paper. It's I think almost 14 orders of magnitude tighter than the micron. So it becomes really tiny. So there, if that was the end of the story, you should basically never expect to see a localized object like this black hole, because it can never fit in the extra dimension. All you would see is this black string that has no features in the circle direction. In that situation, the way we were hoping to understand something about the compact internal dimensions is via the difference between a black hole and a star that could have this scalar hair. So you can imagine two stars merging together to form a black hole, and the resulting black hole could have no scalar hair, which means that all of that has to be emitted as radiation in the merger process. And that's something that it's possible. By the way, this is all speculation. As I said, this talk is about a paper currently being written up. So there's and some speculative aspect of it. So if that were the case, then all of this scalar hair gets radiated away, and we know that LIGO could, in principle, tell the difference. It would see a signal that would tell us that it's not all gravitational radiation that we're seeing, but you can sort of see a difference between gravitational radiation and the scalar radiation. So that would have nothing to do with features in the internal space. But there's another thing which I didn't tell you about today, which has to do with what's called warping of the internal dimension. And warping is sort of in these more convoluted geometries that appear in string theory. Where do we have it? Back there. In these more convoluted geometries, you can have a feature where a piece of this geometry over here gets blown up enormously bigger than you would have thought naively. By enormously bigger, I think we're estimating like 10 to the 40 times larger than the characteristic length scale for the rest of this. So then it suddenly gets kind of interesting to play off these factors against each other and ask, could you have some kind of partially localized black hole in that story that would have features in the internal dimensions and could have scalar hair then? We're still doing those estimates, so I can't tell you whether definitively you could or you couldn't, but I think it's really an interesting possibility. It's never been looked at. So it's something that really should have been looked at, because it's one of the hallmarks of the most believable compactifications out of string theory have that feature, that they can have large warping, very large warping. So it's kind of neat, actually, in that respect. Does that sort of fill in a few more of the pieces?
Yeah, that helps. Sure.
Okay, good.
Are there any other questions? Yeah, Jonah.
Hi, Professor. I'm curious, at the beginning you were talking about the difficulty in experimentally showing this or finding this. Is there some kind of like a Moore's law for experimental observation, like capacity?
Yeah, that's a good, that's actually a really interesting question. So I guess you could ask, is there a Moore's law for like probing smaller and smaller length scales, right? I guess we could chart it and see historically over, I mean, the problem is that, yeah, it probably is some kind of exponential, right? Because technology improved enough, accelerated technology improved enough that you could go to much shorter distances, but then you hit problems going much above a TeV. And the problem is not necessarily that you couldn't go another factor of 10 or maybe a factor of 100. I mean, one of the problems of going up in energy is the cost. So once your next accelerator costs $20 billion, who's going to pay for it? And at what point do you pay for the accelerator over paying for some other societal good, say? And that's what happened with the SSC, which should have preceded the LHC. It was killed, based on cost. But even technologically, if you go up a factor of 10 or 100, you're at 10 to the 12, 10 to the 13, 10 to the 14 EV versus 10 to the 28 EV. So it's such a massive difference in scales that it's just hard to ever imagine probing anywhere close to a fundamental scale of quantum gravity. That looks basically just hopeless. I mean, no Moore's law would really ever get you that. So I think we have to be clever. We have to look for indirect signals from physics that turns that relation of high energy needed to probe short distance on its head. And gravity sort of does that because it's turning high energy into big objects. Black holes have a lot of energy. They're huge, they can have a lot of energy, and it can allow us to explore features of quantum gravity without having to necessarily probe the energy scale of a Planck mass. That kind of makes sense? Yeah, so Moore's law is fantastic. doubling of computer power. What is it? Do you remember the time scale? For fixed cost, you double computer power, what, every
I think it's
18
every 2 years.
2 years? Every 2 years? It's either 18 months or 2 years. But there's no comparable growth, unfortunately, in experiment. Cost, but who knows?
I think Fang Shin had a question.
Hi.
Oh, hi. Yeah, I have two quick questions. What is the physical meaning of the scalar field around the black hole? Is there like a, I don't know, is it a radiation field or other fields? What kind of physical meaning is that?
So good. So Bekenstein's result in 4 dimensions is telling us that a black string that has no features in the hidden dimension would have no scalar field turned on. And he did it as basically an energetic argument. If you try to excite some scalar field in the vicinity of the black hole, the energy was diverging basically. So he couldn't do it. Around the star, you could do it in principle because the boundary conditions inside the star might might make this possible. I mean, in fact, you could, I think, condense the scalar field to form a star. And there are these Bose stars that people have looked at that are gravitating solutions that look like stars but constructed from a bosonic scalar field. And they're actually apparently quite old. They're sort of interesting solutions. I never looked at them until recently. So, but they seem to exist. On the other hand, if you actually have a black hole like this, which is sitting inside, partly localized inside an extra dimension. Now, if you imagine a merger process, say for 2 of these things, or even this in a standard smeared black hole, the merger process could be, 2 of these could be the same point in the internal space, but just separated in space-time. So there could be 2 black holes that in-spiral like this. But that's like the merger process. If you locally look at it and forget the circle, that's like the merger process of 2 5D black holes. So that would emit gravitational radiation in 5 dimensions. So in particular, it would source the metric in the circle direction. And that's the scalar mode from the point of view of 4 dimensions. So really, the fact that it would look universal in 5 dimensions and would source gravitational radiation in 5 dimensions is telling you from the Kaluza-Klein reduction perspective that you're actually sourcing what looks like scalar modes, scalar radiation in 4 dimensions. That's the interesting part of it. So you would source here some, GYY if you wish. And LIGO is actually sensitive to that excitation. So that's our hope. Now, this is all predicated on a bunch of optimistic issues about, there have to be some masses given to these scalars at the end. They can't really be, well, that's interesting. It's not completely clear how small the mass can be. It could be very light mass. So for all intents and purposes, they might be massless. And that would be ideal. Then we really would expect LIGO to see something. But we're trying to kind of set up a scenario where we can start bounding how light the mass is, how many such things there can be. And string theory very robustly tells us there should be lots and lots of these scalar fields. So you have like 10 to the 5th of these scalar fields around, 300,000 scalar fields. That's another augmentation factor on top. So it's not, I think, hopeless that maybe there's something that can be seen here that probes the extra dimension. This is sort of using black hole spectroscopy to explore extra dimensions, or star spectroscopy. It doesn't have to be black holes. It could be some more exotic star-like object too. But lots of possibilities. I think a lot of the physics around gravitational wave interferometry is very incipient. I mean, it's just getting going, and there's going to be very interesting directions to explore. And this is one just directly motivated from string theory. So there are lots of problems here that just classical gravity, a little bit of quantum gravity, and just trying to understand what we can say and not say.
Yeah, thank you. I have sorry for the late. I have one last short question. Does the memory effect has to do with unitarity or the conservation of information?
That's a great question. So tomorrow there is a workshop starting at Princeton on what's called celestial holography. And in that workshop, one of the themes of that workshop is a triangle of relations, which one point of that triangle is the memory effect. Another part of that triangle is asymptotic symmetries. And in gravity, in asymptotically flat spacetime, in 4 dimensions, there's a strange symmetry group. Naively, you would expect Poincare symmetry to be the symmetry of an asymptotically flat spacetime, boosts and rotations and translations. But in actuality, it gets enhanced to something infinite dimensional called the BMS group. So that's another point on that triangle. And the third point on that triangle is what? So, I'm forgetting what the third point is. Soft theorems. And some relation to soft graviton theorems. And Strominger and some collaborators have conjectured, actually originally I guess it was Strominger, Hawking when he was alive, and a guy named Malcolm Perry, made a very bold conjecture that the black hole information paradox, its resolution would require understanding something about these asymptotic symmetries, which in turn would relate to memory, which is the observable really in that case. And so there is a connection to this, sort of through this triangle. I think there's probably I think some people would probably dismiss outright that is the right resolution, but what is clear is that there's a lot of interesting physics around this story of memory. I think there's even potentially interesting physics just for E&M around memory too, which has been discussed somewhat, but not an enormous amount. There's a very related memory effect. It's not a displacement of the particles, but a change in their relative velocity that comes from a kick as an electromagnetic wave goes by, classically. And that hasn't really been put to much use, but maybe there's a way to use it in some experiment and find something interesting out of it. Yeah, so yeah, memory is sort of the observable consequence of having that infinite dimensional symmetry group in asymptotically flat spacetime. Yeah, hopefully we'll see it. I mean, LIGO can see memory even for the standard black hole mergers and the gravitational waves that have been sent out. In principle, it might be observable. There's certainly been proposals to observe it. It hasn't been seen yet, I should say, because it's a very low frequency effect. It's basically zero frequency. So it has to build up, you have to have enough waves go by and build up enough of an effect that you can actually detect it. So for us, memory is a crutch toward a picture of the waveform getting modified by this kind of physics of extra compact dimensions. So the finite part of the waveform, the finite frequency part, will also change in some way. So it won't be just memory, but even memory will change. That's probably the right way to say it. So yeah, good.
Thank you very much.
Sure. Other questions?
Professor, I hope you don't mind me asking another question. Let me see. Like you were like a little while ago, you were mentioning like black hole classification theorems and like how we don't know much about like higher than 4 dimensions. Do you know of any do you have any like good research, good like surveys of like all that we know on that?
So one, I would recommend you come to the Emperon talk. I don't know if it's yet been scheduled, but what's his schedule? He's certainly coming to give the talk. Okay, Zoom.
Okay.
But there is a very nice compilation of results from a couple of years ago in a book by Gary Horowitz. It's a book edited by Gary Horowitz.
Gary.
I don't remember the name of it offhand.
Vacation.
Maybe it might be something like black holes in high dimensions or something like that, which has chapters written by a lot of the people who worked on developing the basic results in higher dimension.
Yeah, that's it. Black holes in Is it 2012 or?
Might well be. That sounds right.
Yeah.
So that's a good place to go if you want to read about. It's a very readable summary I mean, each different sections are written by different people, but
Okay.
they're very well written overall discussions about what's going on in a big picture-ish way as you go about 4 dimensions. This is
Right.
people have found solutions that they called everything from black satins to, I mean, the spherical topology is not the dominant topology, depending on the range of parameters you're looking at, angular momentum and electric charge. You find other more interesting topologies for the black hole horizon, which can.
Interesting.
So that entire zoo, I don't know what the current status is.
Like, I assume they don't get too pathological, right? These topologies.
Well, I think it's
Or
can one classify them and understand what they are in general. So that's a pure general relativity question in high dimensions. How much can one actually say about it? That is typically studied not in the context of compact extra dimensions, but in the context of just 5-dimensional solutions or 6-dimensional solutions, 7-dimensional solutions. This compact business is more around Gregory Laflamme, and there people typically study circle compactifications, but string theory is strongly suggests one should study things that are not circles, and arrives at some of these more interesting features that we're sort of talking about. But the circle is the perfect basic example to understand. So this Gregory Laflamme is the starting point for sure.
Yeah. All right. This book looks fascinating. Thanks so much.
Good. Any residual questions? Are people ready to call in a night?
Yeah. Well, if there are no other questions, let's take this time to thank Professor Sethi. Thank you very much, Professor.
You're welcome. All righty, everyone, stay warm and enjoy the snow before it gets too cold. I think the temperatures are going to drop, so it won't be as warm and fluffy to play with going forward. All righty, have a good night.
Thank you.